My name is Rahmanuddin, and I'm a senior lecturer at Northeast Institute of Health Sciences. Today, we will be continuing with the MRA, the rest of the MRA techniques, magnetic resonance angiography techniques. So, basically, we'll be studying two things today. One is called the phase contrast MRA, and the other is called ECG-Gated MRA. So, the learning outcome of this very lecture will be the phase contrast magnetic resonance angiography. And in the phase contrast, there is another technique, we call it the VENC, which is like velocity encoding. Velocity encoding is very, very important for the phase contrast. So there is a concept involved in the VENC as well, velocity encoding. So we will study that one as well. And the very last section of today, electrocardiography gated fast spin echo and magnetic resonance angiography technique. So while proceeding to our first topic, which is phase contrast magnetic resonance angiography, by phase contrast means that there will be a change in the phase. Change in the phase means that we are having two things. One is called the frequency and the other is called the phase. We are always playing with these two things. So in this technique, we will be playing with the phase. If you bring a difference in the phase, so bringing difference between the two things can give us the contrast difference. So that's how we mean here, phase contrast MRA. Phase contrast MRA uses change in the phase of the transverse magnetization of the blood and form an image. So particularly if we are considering a scenario of the blood, if I give you an example within the brain, so if you target a particular slice, and that slice, there will be some stationary tissues as well as the blood vessels will be there. So in this technique, we are actually, we use changes in the phase of the transverse magnetization. So what do you mean by transverse magnetization? By transverse magnetization, we means if you have given an initial RF pulse of a particular theta, and we give another one, so actually we are bringing the longitudinal magnetization toward the transverse magnetization. So in this technique, if you are changing the transverse magnetization and you are using it in order to differentiate between that of the blood flow and that of the stationary tissues, so that's giving you the phase contrast. So that's the selective phase shift of the moving proton that is produced. We select the moving protons only. We are targeting it. And if you are targeting it, so it can give us a particular image. So this technique is used for the magnetic resonance angiography. What we are using here, we are not using here the spin echo, but we are using here the gradient echo. So by gradient echo, we mean that we will be using the gradients. So if a given strength is applied both on the stationary and as well as on the moving, causing the phase shift between the two, and that differ actually in the contrast, and it gives us the phase contrast imaging. So what do you mean by the GRE? Applying the GRE here is actually, I give you an example of the particular slice. So if you take a particular slice, you apply the RF pulses based on the GRE, which is theta. So there are two type of tissues there, two type of phenomena happening there. One are the stationary tissues, which are not moving at all, and the other one are actually the moving protons. So between them there is a shift. The shift is, there's a difference. The difference is, if you apply the RF pulses, it will be absorbed by the stationary tissues as well as by the moving protons, but the moving protons are not there if you are receiving the particular signal by using the particular TE, because stationary tissues are there. The change will be that will be retained by this particular stationary tissues, but not by the moving one. So that's why there is a difference in between them. So what we are applying here, the initial RF pulse will bring all of the proton in phase. So the all of the proton, by all of the proton means as the stationary protons as well as the moving proton, all of them will be excited and the change will be equal for all of them. So they will be in phase. While applying the second GRE of the same amplitude and the duration as well. Two things are very important. Amplitude, by amplitude we means the strength of it. Are you applying, like I'll give you an example of +1, +2, or whatever you want to do. So the amplitude should be the same as well as the duration, for how long you are applying, for how much time you are applying. So those are applied. The first GRE is the second GRE. Both of them are applied in the opposite direction. One in the positive direction, the other should be in the negative. For example, if you are applying one in the positive direction, it will be +1. So you will have to apply -1 in order to actually compensate it and bring it to the original position. So this is a typical example of the phase contrast MRA. Have a look at the bipolar gradients. Bipolar gradients means that we can apply in both poles, as well as in the positive as well as in the negative. So you can apply in the both poles, positive pole or either the negative pole. So looking at this first polar gradient, which is in the negative direction, for example, I'll give it in the value of -1. So have a look over here. There are the blue line represents the stationary spins, and while this red line represents the moving spins. The moving are the blood spins. The spins, by spin we mean the protons, as you are well aware of it. So applying gradient in the opposite direction will bring the change in the stationary as well as in the moving protons. But have a look at this stationary one. It comes to a particular value. If we apply the same gradient in the opposite direction, so this change will be compensated. As you can see, if you draw this line, so it will come to this original line. That's how the change will be compensated in the stationary one. But the case will be different in the moving spins. Why is that? Because the moving spins are moving. They are not static. They are not in one place. So the change it carries, it will be moving. It will take it with with those spins. So the difference happens between the two things, the moving spin as well as in the stationary spin. For example, the change in the stationary spins at this particular level will be 0 because we have applied in the negative direction and in the positive direction. The net change for the stationary is 0. But now looking at the case of the moving spin, so if you have applied the particular gradient in the opposite direction and then that in the direction opposite to the initial one, so the change is visible. It will follow the path just like this, and then there is a net phase difference between the stationary spins as well as in the moving spin. This is the initial condition where they will appear as a darker one, and this change actually represents that the moving will be having a brighter appearance. So this actually gives us, this particular phenomena gives us a difference, and the appearance between the stationary and that of the moving one will be different as well. So this type of imaging is called phase contrast. Now in the stationary, for example, there are two at this particular, for example, at a particular slice, there are stationary protons. So the reversal of the phase shift will occur on the exact amount as you have applied the earlier one. So cancelling the effect of the original phase shift, as you have seen. How? Here, if you have applied the phase shift of -1, if you applied, and then later on we apply using the bipolar gradient in the opposite direction. So the net change for the stationary will be 0. So that's why we say that the cancelling the effect of the original phase shift resulting into no net phase shift. So the difference is in between the stationary and that of the moving one, and the stationary will appear as a darker one, and the moving one will be having some contrast to it, and the contrast is it will appear as a bright one. So the flow proton change their position and the phase shift will not be corrected at all. So as you can see, it is not corrected because it's the corrected, we will be calling it a corrected if it follows this path, is the stationary one is following. So it's not following that one. Now this phase shift is directly proportional to the change in the location, the distance or the distance. Location or the distance, the proton travel between the application of the first and the second gradient. Now, this very particular phenomena, it is directly proportional to the frequency, to the velocity actually. What do you mean by velocity here? For example, we are having a different flows in a different artery as well as in a different, location. For example, if you are measuring the velocity of the aortic abdominal thoracic aorta or that of the peripheral artery, there is a hell of difference between the velocity in between them, as well as the difference between the velocity of the veins and the arteries is there as well. Similar is the case with the, if the artery is very near to the heart, it will be having a more velocity compared to the one that they are far away from it. So that's why the difference is there. So there is a particular phenomena over here. The phenomena is called VENC, which is VENC. I'll show it. I'll show that one in the next slide. The phase shift is caused by the PCMRA to create the angiographic image. Why we are using this phase shift? Why we are using this bipolar gradient? We are using it in order to get the angiographic image and to measure the flow velocity. How? This particular VENC is very important for the PC to happen. The PC MRA, this PC, phase contrast MRA, it will never happen until unless you use this VENC called velocity encoding. What is velocity encoding? So have a look at this particular image. We are having this bipolar gradient as we saw in the earlier one. The one in the opposite, either you call it -1 or this called +1, or you call it +1, this -1, doesn't matter. It's a bipolar gradient. Bipolar means one is having the pole opposite to the other one. So both of them will be having opposites one. Now we are considering a particular slice. For example, in this way, we are having a stationary spins, and in the arteries we are having the moving spins like the. If we apply a particular, the first lobe, the first gradient is applied. The first gradient is applied, the change will be similar for both of them. How? Have a look at this. The spins are in the longitudinal magnetization. The longitudinal magnetization for the moving spin as well as for the stationary spins are at the maximum. But if you apply the gradient, both of them will be shifted in this direction. So same change happen at both of them, at the stationary spin as well as at the moving spin. But you know that there is a change that is happening. For example, this particular blood is flowing. So if it is flowing and we apply the second lobe, which is like the gradient, what will happen? Straight away, this will return to its original position, which is like this one. This is its original position of the stationary one. But while following the path by the moving one, it will never recover to its original position. But either it will slowly start to recover because the change will be, because it's moving. So it will not carry the changes that is being created by the stationary one. So have a look. The change will be only this much. It will return only to this point. That's why this particular phenomena is similar to this one. Stationary change is like, there is a particular change that happened in the opposite direction, and compared to this one, you apply an opposite to this one, and the change will be, then there will be a net effect of 0, but not the case for the moving spin. So that's why over here, the case is not for the moving spin, because there is a change in the in that particular gradient you apply, because this one will follow the original path that is returned to its original position, but this doesn't come to its original position, as you can see the difference between them. So this change in the contrast between them, we are using it for the imaging purpose in the phase contrast imaging. Okay, velocity encoding gradients are applied in one or all three directions to acquire a quantitative information. Now, what do you mean by gradients applied in one or either in the all three directions? So by that we means only we are applying it for the phase gradients only, or either we can apply it for the frequency encoding as well as for the slice selection. So if we apply all of the three, we call it the all three directions. Or either we are applying it only in one direction, which is the phase one, so we call it the one. So that's how it varies between them. Either you want to use it for one, or either you want to use it for all of them. Velocity encoding technique compensates for projected flow velocity within the vessel by controlling the amplitude and strength of the bipolar gradients. So the case will be, if you are applying, this height represents the amplitude, represents the strength of this particular gradient. and change from here to here, it is called this is called the time. So the time and the amplitude, that is very, very important. Like you will have to apply, not like you can't apply half of it in the next one. No, you will have to apply having the same amplitude, having the same, time, or either the distance. The time is actually the distance from here to there is actually the time, or either the distance. So both of them should be having equal and opposite value. So if velocity encoding is selected lower than the velocity within the vessel aliasing velocity. Velocity encoding is something that you will apply a particular velocity. So how did we get those velocities of the particular arteries? So we have measured them using using a research. Like by the research we know that this particular artery or vein is having that much of the velocity. So if you apply and if you have selected this VENC velocity encoding is a parameter that you will have to use it before the PC MRA. While you are performing the PC MRI technique or either the particular imaging, before that you will have to give this value. We call it the VENC value. So if you select the velocity less than that of the particular vessel, because every vessel is having its own velocity, then the aliasing will happen. And aliasing is an artifact. Aliasing results in low signal intensity in the center of the, what is aliasing? It's having a low intensity in the center of the vessel, as well as better delineation of the vessel wall. So how do we select these flow encoding? And by this, we mean one or all three direction. We mean here you are applying it in the gradient of the slice selection gradient, as well as in the phase gradient selection gradient, as well as in the reading gradient, which is x, y, and z. So you are applying flow encoding gradient and one in the opposite direction, in the positive direction, the other in the opposite direction. That's how the change will be constant for the stationary, but it will not be followed by the flow blood that is flowing, the spin that is flowing. So if you achieve this particular image or either the signal, there will be a difference between the stationary and that of the moving one. So the typical values for the velocity encoding gradient, velocity encoding are for the venous flow, it's 20 to 30 centimeter per second. The as we know that the term VENC stands for the velocity encoding. So velocity, the unit of velocity is centimeter per second over here in the MRI if you are using it. So that's why we are measuring it in centimeter per second. So venous flow will be from 20 to 30 centimeter per second in the venous flow. And for the higher velocity with some aliasing are 40 to 60 centimeter per second. In order to determine velocity and flow direction, we are using 60 to 80 centimeters. We can also measure the velocity out using this particular technique. So PCMRA provides information about the flow direction. That's how the difference comes. For example, in a very particular slice, if you are having two, things. For example, the flow of the arterial flow is there, either the oxygenated blood or the deoxygenated blood. It is being carried by the venous system. So you can find the difference between in the direction of the flow. For example, is it the direction of the blood, arterial blood that is happening, or is it the venous blood? Because when we select this particular technique, if the flow is encoding from the superior to inferior, it means, for example, if I take an example of the particular neck area. In the neck area, we are having two veins that are the vein and the artery that is going side by side. One is the carotid artery and the other is the jugular vein. So if you are measuring if the flow is encoding from the superior to inferior, means if it is bringing from the head toward the neck side, that means that it is the venous system that we are looking into. Because in this phase contrast imaging, we are not only taking we're not only imaging the arteries, but we are also imaging the veins that we like. but it's up to the direction, in which direction we are selecting this particular, study. So the head will appear bright and the feet will appear as a black. So this is an example of the whole body imaging. If we are taking, the head will appear as a bright one and the feet will appear as a black one. PCMRA can be acquired in two-dimensional as well as in three-dimensional. Two-dimensional is used in routine practice, but because of the acceptable acquisition time is 1 to 3. As we know that when we are going toward the higher technology, it needs a lot of time as well as the technological demand is there. So two-dimensional imaging, we are having, why we are using two-dimensional at certain time, we are using it because we want to see the particular type of imaging in a very short time. So that's why the acquisition time for this one is 1 to 3 minutes, which is less. We are having a patient burden in the hospitals as well. So for that case, you are having both of the option. If you are working in a standard way of examination of the person, of the patient, so it should be three-dimensional, because the three-dimensional can give you a lot of information. Okay, so in the phase contrast imaging, if I give you an example of the, for example, we studied that for the slow flow is this much and for the other one is that much, but looking at the typical particular areas, for example, the aorta, the MPA is main pulmonary artery, and the aqueduct. So have a look, there is a hell of difference between all of them. For example, aorta, where there is a high blood flow that is happening because near to the heart, it takes the blood in a systolic way, like systole is having a high pressure. So that's why the velocity for the aorta is 150 centimeters per second. While NPA is a main pulmonary artery, which is like taking the blood from the right side of the heart toward the lungs. That's why it's also higher, but it's not that much higher as compared to the aorta. So the flow velocity for this one is 120 centimeters per second. Now, looking at the aqueduct, I know you are well aware of the aqueduct, anatomy of the aqueduct, where the aqueduct is. Aqueduct is between the third ventricle and that of the fourth ventricle within the brain, because the CSF flow happens there. This aqueduct is very, very important, because certain time internal CSF pressure rises in certain children and as well as in a lot of patients. So for that case, in order to see the flow within the aqueduct, we should need to know that what is the velocity of the aqueduct. So this is very important for studying the CSF flow around this particular CSF system. CSF system, the CSF system is between the third ventricle and that of the two ventricles, the lateral ventricles, between the second, third ventricle and the fourth ventricle, between them is the aqueduct, as well as it flows down toward around the spinal cord. So that's why it's very important for certain studies as well. So we should be aware how much velocity is there. So these values for the velocities are very important to be remembered. This is the phase contrast imaging. So you can see this particular anatomy is of the brain, but we can see the sagittal sinuses and the transverse sinuses of the brain, that the venous flow is happening actually there. So that's the typical image for the phase contrast MRA. Okay, now we will move toward our last one and the most important, the ECG-Gated fast pen MRA. As you know, ECG is electrocardiography. Electrocardiography is that you are using the leads and you can measure certain changes or either particular phenomena that is happening. So we are having in each of the cardiac beat, there is a particular signal that is formed, and we call it the PQRST. And the PQRST, it represents a particular phenomena, like when the systole is happening, the arterial filling is happening, the systole is happening, the diastole happens. So it gives us a whole story of it. So ECG-Gated FSE MRA is using the electrodes. Look at the electrodes. There are three colors of electrode. One is the white one, which should be placed between 2 to 4, left parasternal space. We use it in this particular area, and then the green one below the zipisternum there, and below the nipple we use the red one. So these are the 3 leads that are being connected to a patient when you are doing an MRI based on the ECG-gated one. So in this technique, images of the vessels are required in systole and diastole. So there are 2 techniques. There are 2 phenomena that happens. One is systole and the other is diastole. By diastole, we mean that the heart is being it recovers to its full, full diameter, like start to actually takes of the particular image. We call it the relaxation of the heart. So we also call it the diastole. In a systole, it's actually the contraction of the particular, for example, you are taking example of the right ventricle or left ventricle. It's up to you. For example, in the if you are measuring for the main pulmonary artery, so you will have to consider the right side of the heart, so which is the right ventricle. So if right ventricle takes up the blood, it reaches to its maximum capacity. We call it the diastole. And if the contraction happens, we call it the systole. Or either if you are taking example for the aorta, so similar is the case if you are considering the arterial flow. So you will have to look at the left ventricle side. The systole will be the contraction, and the relaxation is the diastole. So we take 2 type of imaging, one in the diastole, the other in the systole. But there is a particular phenomena that is happening. For example, if you are using the ECG-gated FSE MRA, so if you are using the FSE MRA in the diastole is actually the relaxation of the chambers. Or either if you are taking this, if I'm giving you an example of a particular artery or vein, the diastole, both in the arteries as well as in the vein, they will appear as a bright one. But in the systole, the flow will appear as a black one, because in the systole, the blood is moving fast. So if the blood is fastly moving, the protons and the spins are fastly moving. For that case, it will appear as a darker one. So in the arteries, they will appear as a black one, but while in the veins, they will appear as a bright one. So in this diastole, if you look at the diastole, the arteries, vein, both appear as a bright one. In the systole, only the vein appears as a bright one, but the artery will appear as a darker one. So where is the difference? The difference is in the systole, not in the diastole, because in the diastole, both of them appear as a bright. In the veins, both of them appear as a bright one. In the diastole, the artery appears as a bright one, but in the systole, the artery will appear as a darker one. In the diastole and in the systole, the vein will appear as a bright one. So the difference comes between only the arterial flow, which is like bright in the diastole and darker in the systole. So if you subtract an image of the diastole from the systole, it will give you a bright blood arteriography. Because if you look at the veins in the diastole and the systole, if you are subtracting from each other, it will give you no image at all. Why? Because both of them appear as a bright in the diastole as well as in the systole. So in the systole, images are subtracted from the diastole imaging, resulting in the bright blood in the arteriography. So that's actually forming the basis for this particular imaging. Now look at this one. We are having P, Q, R, S, and then there is a T. So this very particular imaging, we are having 2 areas which are very important for us. One is this, we called it the end diastolic area. This is the end diastolic P here. So end diastole happens here, and the end systole happens when the T wave is ended. So if we subtract this end diastole from end systole, it will give us a bright image of the arterial system only, not of the venous one. So that's why it's very, very important. Okay, this the area between the S and T is the systole. The systole actually happens here, but it actually finishes there. That's why we call it the end diastole, end systole area. End systole is very important for us, and end diastole is very important for us too, because in end systole it is the maximum contraction that it carries, and in the end diastole that is the maximum relaxation that it can take. So it gives us the information of the its maximum value in both of the phenomena, either in systole or in diastole. So what are the advantages of this particular ECG gated? Relative short time we can get it, because PQRS is very fastly happening phenomena. We know 72 beats per minute is happening. So that's why it is having it can be achieved in a very short time. Sensitive to slow flow. Obviously, if the slow flow is happening, what will be happen? We know venous flow is also slow flow. Slow flow will appear as a bright on systole as well in diastole. So it will not give us any difference in the image. So both of them will be, if you subtract it, it will give you no image at all, a darker image, because the white will be subtracted from the white one, because both of them appear as a bright on systole as well and diastole. And this is acquired in the coronal plane. Why? Because the heart is, you can't take maximum information from the heart in the other two planes, like that of the sagittal as well as in the axial one. But you can take maximum information from the heart on using the coronal one, because you can see all of the chamber, the filling within the chambers. So that's why they acquired in the coronal plane. While this particular PQRS technique and this end diastole, end systole, and this ECG getting imaging is only possible in normal patient, not in the arrhythmic patient, because in arrhythmic patient, this it's arrhythmia. The heartbeat happens irregularly, so you can't differentiate between the two. That's how you can't. There's a limitation for this particular of this technique. The limitation in the arrhythmic patient. Used in the peripheral arteries and the aorta, you can use it for the peripheral arteries as well as for the aorta. We call it the HBI and Toshiba, native space in the Siemens, and trace in the flow preps in the other particular imaging technique. ECG-gated fast spin echo MRA. So have a look at this particular artery. Artery appears here and the vein is there. So this is the diastole. In diastole, both appear as like this one is this one and this one. Both of them appear as a bright one. But have a look at this. In the systole, and the systole happens. The systole is artery. The artery appears as a black one, and the vein appears as a bright one. So if you subtract the two images, it will give you an image of only artery, because the white and the black, the difference between them, if you subtract it, it will become bright one. The rest of them, they are having the same anatomy, because in subtraction, all of the similar anatomy will be subtracted. So have a look, all of the similar anatomies are being subtracted. Only the arterial image is formed. So that's how it forms and give us a basis for the ECG-gated fast spin echo MRI. Thank you very much.